Hello, I'm Michael O'Connell, and in tonight's video we're going to be deriving an expression for the fanning friction factor for laminar flow. Here on the board I have a cylindrical pipe drawn in which I've selected a controlled volume of fluid, a concentric cylinder within the pipe, of fluid that is flowing down through our pipe through an altitude change denoted by delta Z. This fluid is at steady state, and it's also Newtonian fluid. Both of those facts will be important for us when we derive this expression for the fanning friction factor. Now, when we have a fluid at steady state, we know that Newton's second law, where we describe the net force acting on our controlled volume of fluid, is equal to zero. This makes sense because the acceleration, which is the differential change in velocity over the differential change in time, is zero because all derivatives with respect to time go to zero when we're at steady state. Okay? So we need to figure out what forces are acting on this controlled volume of fluid. Now, I always like to start with the pressure forces. So we have a pressure force on the top, and we have a pressure force on the bottom because both of those are exposed to the atmosphere here. So that means that the pressure force there is due to the atmosphere, and the pressure force down here, the force is upward, by the way, even though it's at the bottom here, so upward against the flow of our fluid, is also due to the atmospheric pressure. You might be wondering how this is possible, right? How is there not a pressure increase, right? We decrease potential energy, you might expect a little bit of pressure recovery, right? Applying Bernoulli's equation. But that's not going to be the case here, okay? In the past, we've looked at this expression. We've looked at this in at least one video thus far for transport, and this is the basic equation of fluid statics. So it doesn't apply here because our fluid is in motion. We have fluid moving down through this pipe, so the fluid is not static, that is for sure. So this expression does not apply, and we do not see a pressure increase as we move down this pipe. Also, it is important to know that we are going to be applying Bernoulli's equation in this situation. And as I said here, with steady state and given the continuity equation that these areas are the same, okay, the cross-sectional area of the cylindrical pipe, and of course for our controlled volume as well, there is no change in velocity, right? The continuity equation, volumetric flow rate, is the velocity of the fluid multiplied by the cross-sectional area. Okay, so if this doesn't change, this obviously is not going to change. We do not see a change in velocity, right? So the only thing that is driving this is this change in potential energy, which leaves us with that fancy F that's on the right-hand side of Bernoulli's equation, which we actually ignored in the last video with the rotometer problem. That is the frictional heating. Okay? And actually, on the right-hand side, it's expressed as negative. Okay? And then all we're going to have there is that change in potential energy that we see. Okay? But we're not there yet, right? We need to do a force balance. So, if I'm telling you that there's no change in pressure, so we don't have to consider pressure forces, what forces do we have to consider? Well, this is in the vertical position, right? So we do need to consider the weight of our fluid, okay? We know that this is the mass multiplied by the acceleration due to gravity. We express the mass as the density of the controlled volume of fluid multiplied by the volume itself. The volume, we know, is going to be the area, okay, from the top view. So this is the area of a circle, right, pi r squared, where this small r is going to be used for the radial position within our fluid that's moving down through this pipe. Large R we're going to actually use to denote the radius of the cylindrical pipe itself. And then when we're talking about the volume of our controlled volume actually that we selected, we need to account for all these circles moving downward through some altitude, right? And that's going to be delta Z. And we know this expression, right? This is the volume of a cylinder, okay? But that is going to be specifically our controlled volume. that we need to put here, okay, because we're trying to account for the weight, which is the volume multiplied by the density. Okay, hopefully that's visible on the end there. It looks like it is. Okay, so that's your volume. Then, of course, don't forget the acceleration due to gravity. Now, there is another force that we have to consider here. Okay, you would have to ask yourself, based on what I revealed before getting to this expression for the gravitational force on our controlled volume, where or from where does the frictional heating emanate? Well, that comes from the viscosity of our fluid, okay? So these layers of fluid are rubbing against one another, right? So let's look at our controlled volume. So we have fluid just inside our controlled volume moving downward through the pipe, and fluid just outside the controlled volume moving downward through the pipe. Okay, this fluid that is just outside the controlled volume exerts a shear stress, that is a pressure force. I shouldn't say pressure, it really is a stress, and I want to say that because that force, that shear force, is exerted along a surface, whereas the pressure forces like here that we always talk about are exerted normal to a surface. So that's extremely important. So now we need to look at the velocities, okay? And this is where this comes into play, right? We have a Newtonian fluid. So Newton's law of viscosity has the shear stress, which is equivalent to sigma. That is the shear rate multiplied by the viscosity of your Newtonian fluid expressed as mu. This shear rate is equal to the differential change in velocity over the differential change in radial position. Okay, so if we're moving outward to a position that's just outside our controlled volume, this is negative, right? And the velocity specifically that I'm interested in here, the velocity of this fluid that's just outside our controlled volume is lower, okay? Now, what does that mean? Well, what that actually means here is that it's dragging, okay? It's exerting a shear force against the downward motion of the faster moving fluid inside our controlled volume, okay? So that can be kind of confusing, right? So again, I'm going to repeat it one more time. So we have fluid moving faster because it's at a smaller r, right? It's closer to the center here where r equals 0. Again, as we move radially outward, the velocity of the fluid decreases, okay? So then we have a layer of fluid that's, rubbing up against this layer of fluid that's inside our controlled volume. And because this is at a larger r, right, the velocity is smaller, okay? So it exerts a shear stress force upward against the downward motion of the fluid inside our controlled volume. And that is the layer fluid that's just inside, just to be specific, because again, it's the viscosity of this fluid that's causing the frictional heating, right? Okay, so what does that mean for us? Well, that means that this shear stress, this has to be added on, specifically, of course, the force, because we're performing a force balance, okay? And again, we know that our net force is equal to 0. So we already have this expression for the weight of our fluid. We just have to consider how we would express the force due to the shear stress that's exerted by the fluid on itself, right? And I already revealed this, didn't I? Because we have tau, that's the shear stress itself, okay? Which, hopefully you remember that would be in these units, right? Newtons per meter squared. Okay, so of course we need an area here. So what is that going to be? This is where we have to be a little careful, right? Because as I said, a shear stress is exerted along a surface. Okay, so we need the surface area here. So specifically here, with our controlled volume, we're going to be concerned with the circumference. Okay, and then that we will multiply, of course, against this change in altitude, okay? Because this would just be one dimension, right? And then we move all the way down to get that surface all around our controlled volume at some radial position r, okay? Which is why we'll use the small r, okay? So this would be 2 pi r times delta z, and then that is set, oh boy, I ran out of room. That's set equal to 0, of course. Okay, what do we want to do next? The next thing we want to do is express this. This is the shear stress, okay? And once again, we've already looked at this equation. This is a Newtonian fluid. So we know that we have the shear rate, sigma, times the viscosity of our fluid, okay? Now, this is going to be the differential change in velocity over the differential change in radial position. Ooh, that is just the wrong way to draw that. Multiplied by mu, the viscosity of our fluid. So this is substituted into here, okay? Now I'm going to take some time to erase, but what we're going to do here is actually find an expression for the velocity. Now that I've gotten a chance to erase everything, I'm going to rewrite what we had on the board before. And remember that I'm substituting for the shear stress using Newton's law of viscosity. Okay, so we're going to write this expression for the net force. Now, the next thing we want to do is we want to derive an expression for the velocity of our fluid as a function of radial position, okay? And this would actually allow us to graph the velocity profile of the fluid that is flowing down through our pipe, which I think is pretty cool. So how would we do that? Basically, we would want to move this term to the other side, right? And we would get some cancellations. So I'm going to derive that expression here, where I'm going to be solving for the shear rate, the differential change in velocity over the differential change in radial position. Now that we have this expression, we're going to do something a little bit different than what we normally do. Obviously, this is in the form of a separable differential equation. But this time, we're just going to integrate both sides now. Okay, so we are going to get a constant of integration that we'll have to deal with. So because we did not use the method that we usually use to solve separable differential equations, and we don't have our bounds of integration, of course, this term, right, this will become our velocity, okay, which is kind of good because, again, we want to express this velocity as a function of the radial position. These are all constants, right, that would come out, okay? So we can rewrite those down here, and then we integrate this r, okay, so that's r squared over 2, okay? So this down here, this becomes a 4. Excellent. So that's our expression for the velocity. Now again, don't forget this large c, right? This constant of integration. How can we find that? This is something that I wanted to mention earlier when I was talking about the shear stress that is due to the viscosity of our fluid, because that emanates from the contact between layers of fluid, right? And I also talked about the difference in speed based on the radial position causing that shear stress, wherein the slower moving fluid was actually exerting a shear stress on the faster moving fluid within our controlled volume. So here I would ask, well, this is actually a situation we've seen before. So within our cylinder, right, let's say our cylinder here, the pipe I'm talking about, has a radius large r. What is the velocity of the fluid at the surface here? So when we have a fluid moving along a surface, the velocity of that fluid is equivalent to the velocity of the surface, okay? And that is the no-slip boundary condition. Once again, the velocity of a fluid that's moving along a surface is equal to the velocity of the surface, okay? And here, the surface for a cylindrical pipe is 0, okay? So V equals 0 when little r, which is our radial position, is equal to large r. So we can use this, right? And we can actually find the constant of integration. Okay, so we can set the velocity equal to 0, and then all we do here is plug in little r. We would have the large r, the radius of our cylindrical pipe there, okay? And we see here that this is very, very non-trivial, right? We move this term to the other side, and we have our constant of integration. Okay, so that would lead us to this expression. Okay, So we would have all the same terms, of course, except we have the large R. Okay, so this would give us this expression for the velocity as a function of radial position. So we have these constants out front, and then we have the large R squared minus the small r squared. Okay? Awesome. So this is very, very good, right? This is exactly what we want to see. What else can we express here, right? As I said, we could graph this and actually get at the velocity profile of the fluid that is flowing down through a pipe. Remember that this is laminar flow. Now, what's really interesting to think about here is that, again, the largest velocity you see is actually in the middle of the fluid, right? Where small r here, radial position would be 0, right? And notice again that this term is subtracted, right? So any other non-zero term, any other radial position that is, some distance from the center of our flowing fluid down through this pipe is going to make your velocity smaller, okay? So that's interesting to think about. And as I said, with the no-slip boundary condition, the velocity of the fluid that's moving along the surface, right at the surface of our cylindrical pipe is 0. Okay, now that makes sense, right? Because this would be large R, and so this expression for the velocity would be 0. Okay, so that's consistent. What else can we get at here? We can also get at the flow rate, right? We know what the flow rate is. Okay, now here you would have to apply an interesting concept that we already really know, right? We already have an expression for the velocity as a function of radial position, okay? But we need to account for how the area of our fluid changes with respect to the radial position as well. So this expression works, right? The velocity times the area, but again, we have that area changing as we move radially outward, okay? So we would really express this here. And of course, our velocity depends on the radial position as the velocity multiplied by the differential change in area. Okay? Now, what would that look like for us? This isn't too hard to imagine. We've done something like this before, I believe. So if we're looking down our cylinder, okay, we are going to take out a small cross-section, right, of thickness dr, right? Again, some small change, some differential change in our radial position. Okay, and then of course this is going to be multiplied by the area here. Again, you can think of that as the thickness. Sorry, not the area. This would be the circumference, right? And then this is your thickness that gives you the differential change in area. Okay, so this would be expressed as V times 2 pi r dr. Okay, now this is good because we already have an expression for the velocity as a function of radial position. So we just need to plug that in, okay? And let's see what happens here. Now, what's nice is we can move this out, okay, of the integral. Okay, so the 2 pi comes out. This cancels with the 4. Okay, so we get rho g over 2 mu. And then make sure you don't forget the pi, of course, and I'm really saying that for myself, obviously. Okay, so if these are taken care of, what's left is this r squared minus r squared multiplied by r. So that is what we get inside here. And then we are integrating with respect to the differential change in r. Now, with that situation I was looking at here, when we're looking at the top view of our cylindrical pipe, our largest radius is r, and then the smallest we can be is right in the center, which would be 0. So these are our bounds of integration, right? We have fluid within this pipe, and it is flowing into the screen for you here down our vertical pipe. So these are our bounds of integration, large R and 0. Okay. And again, those are for this, the radius. Okay? So what can we do here? Well, I actually should have multiplied this in, right? So let's actually re-express that. So that's a little r squared minus r cubed. Okay? And what do we want to do here? Well, we want to integrate. So I am going to do that real fast here. Okay, so notice here these are our bounds of integration that I plugged in here, and this becomes r to the fourth over 4. Okay, so now I should have written this on our left-hand side. We have an expression for large Q, the flow rate. Okay, r to the fourth, and then we have this 4. Don't forget to multiply that against the 2, 8 mu. Okay. Now again, because we're ultimately going after the fanning friction factor, we're actually going to want to re-express this in terms of the diameter. Okay, so I'm going to take some time to erase all of this here, and then we will continue with this derivation. I'm going to express the volumetric flow rate in terms of the diameter of our cylindrical pipe. So this would be large D over 2 to the 4th power. So 2 to the 4th power is 16. 16 times 8 is 128. So Q becomes pi rho G times D to the 4th power. And then we have 128 multiplied by the viscosity of our fluid. Okay? So where do we go from here? Basically, now we need to talk about Bernoulli's equation. Okay, I've referenced it before, and I'm referencing it again. Okay, so this expression here should be familiar, and it's not as scary as it looks. Okay, and this fancy F always gets me, but that is the frictional heating, and that is not negligible in this case. Okay, so here, we don't have to consider any change in pressure, right? There's no increase in pressure as we have our fluid move down through this pipe. And then there's also no change in velocity because the cross-sectional area of this cylindrical pipe is constant. And again, remember, the lack of change in pressure is due to the fact that we have our fluid in motion at steady state, and each end is exposed to the atmosphere. So you have the pressure force due to the atmosphere on both ends of our fluid. And then we have the change in altitude, right? We decrease potential energy. So this delta Z is actually negative, and this moves through, we could say, the length, L. Okay, so because there's a decrease, right, this would be negative L. It would be the opposite of the length, okay? Again, because the altitude is decreasing as the fluid moves down through the vertical pipe. Okay, so we have this expression here, and this is set equal to the frictional heating. Okay, now this is really good, right? Now we don't really know this, right? But we need to get an expression for the frictional heating, and we can do that, right? Because we can rearrange this expression of the volumetric flow rate in terms of the acceleration due to gravity. Okay, and that's exactly what I'm going to do. Now we're ready to continue. Once again, I'm going to take some time to erase all of this, and then we are going to continue on with this derivation. And specifically, we're going to have a very, very interesting and important equation for the frictional heating. Now we're ready to make our substitution. So we have the acceleration due to gravity, and we can substitute that in here. Notice that the negative signs cancel. And then notice that I've also added here the frictional heating expression that we're going to use that has this small letter f, and that is the fanning friction factor that we're after. Okay, so using what we already have here, we can express the frictional heating here. Okay, and this is from this expression that we have, and then we can set these equal to one another, right? So for F, L, and then the V squared over 2. Notice that this 2 here, that's not squared, okay? So let's make some cancellations before we continue. So 4 and 2 cancels to 2, and then the 2 here, we cancel that out, so this becomes a 64, and then we have mu q that stays, the L's cancel, okay? Obviously, we're trying to isolate F, which is our fanning friction factor, And then we have the v squared. Again, that's going to be part of this denominator here. The pi stays, the rho stays, okay, so we've used those, and these cancel as well, so that we have the diameter of our pipe cubed, okay? So notice that this expression had the diameter. That's why we made that change with the volumetric flow rate equation, in which we re-expressed it in terms of the diameter d. Okay, so we used the velocity squared, we used mu, we used q. Okay, and this is equal to the fanning friction factor. We're not quite done yet. There's actually some simplifying we can do. Okay, specifically we know that the volumetric flow rate is equal to the product of the velocity and the cross-sectional area, where the cross-sectional area is equal to pi d squared, d being the diameter of the cylindrical pipe, over 4. Okay, so what does that give us? Well, that 4 and the 64, right, if this is q, okay, those cancel. Okay, so we have a 16 there. These pi's are going to cancel. And then the d squared and the d cubed are going to cancel. Okay, so we're going to be left with a d on the bottom. And then, actually, the other thing I forgot, this accounted for all of our area. We have this velocity here within our q. That cancels with v squared. So this velocity v is just left there. In the bottom, we have rho, which is the density of our fluid that stays, and then we have mu. We've already taken care of all the volumetric flow rate terms, okay? And then this is basically our final expression. What's really cool about this is that the Reynolds number is the diameter multiplied by the velocity of the fluid multiplied by the density divided by the viscosity, okay? Now, remember, you also have the kinematic viscosity that you'll also see this expressed in, and I believe that that is, I forget, I want to say it's the viscosity divided by the density. Okay, so that would make your expression, let's see, flipping that around, it would be dv over nu. By the way, that's the Greek letter nu. I'm very bad at drawing that, but that's just something I wanted to mention, that you might see Reynolds number expressed with the kinematic viscosity. But again, this expression is the Reynolds number, okay, which is dimensionless, okay, and that is right here, okay, inverse. So the fanning friction factor for laminar flow, of course, is 16 over RE, which RE is the Reynolds number. So we have successfully derived the fanning friction factor. Thank you so much for watching. I just want to end this video with an apology for the bad quality of the last video in terms of seeing the board. So in this video, I tried to change the lighting and make it more visible. And I also bought markers this weekend, which is really nice. And I think it actually does look a lot better. So I hope this video was a lot easier to follow. Unfortunately, this was honestly a longer derivation than I thought. I just had a lot more to say and explain. But again, if you're wanting to have this written down again, this expression, the fanning friction factor, is equal to 16 over the Reynolds number for laminar flow, of course, in this situation. We could have also derived this looking at a horizontal cylindrical pipe as well, and of course looking at the controlled volume. Now, in that case, you actually would be looking at a pressure drop due to the frictional heating, which of course emanates from the viscosity of the fluid. And in this video, I just chose to go with the vertical cylindrical pipe. So thank you so much for watching, and then I hope to see y'all next time.